Hey everyone, have a new lesson for you. You'll have to excuse me. I'm recording pretty late in the day, so if I yawn or seem a little bit tired, I apologize in advance. But let's get started. As always, hope you're healthy. Hope everyone, all your loved ones are doing healthy. So let me know if you need anything. But let's get started with this. We're gonna continue with trig and the right triangle. Basic right triangle things we were doing. So this is pretty much chapter 13-1, which is a quick look into right triangle trig. I'll post the notes that I hand wrote, but this is going to be a little bit different from what we've done before. I'm pretty much just going to write as if I'm actually able to teach, on a whiteboard. So it'll cover most of the notes, but I'll do a little bit more examples here or explain a little bit more in detail too. So this is trig 13-1. All right. So continuing off of everything you know about right triangles, again, the biggest thing is the Pythagorean theorem, but a lot of times, you're going to need more than that. So the Pythagorean theorem obviously works if you don't know one of the sides, right? So that means you have to know two of the other sides of a triangle. So you get a right triangle. If you know two of the sides, obviously you can use the Pythagorean theorem to figure out the last one, right? Now, the whole beginning of this chapter is talking about the trig functions. Okay, so there are three main what we call trig functions or ratios. Okay, and you'll see why they're called ratios specifically in a sec. And again, ratios just means it's a fraction, right? There's something in relation to another. So there's a numerator and denominator. So there are three main ones. Now, the biggest thing is we're going to use this symbol, which some of you might have ever seen before. It's called theta. Okay. It's Greek. I'm pretty sure it's Greek. It's just like a variable. It's just a symbol like X, right? It's just a variable. So we use theta just because that's what's common when you're talking about angles. So like I said, triangles have three angles inside. One of them is a right angle, and the two others, typically you don't know what they are. Sometimes you will know what one of them is, but when you don't know, just like when you don't know a number, you call it X or Y. When you don't know the size of an angle because it's in degrees, usually it's a little bit different. We just use the symbol theta. Okay, so a little bit different there. All right, so there are three. Let's write this again. So the three trig ratios. All right, so three trig ratios. First one is called sine. Second one is called cosine. And the third one is called tangent. All right, and we abbreviate these. These are also all on your calculator, your graphing calculator. They're all buttons on the calculator. So we abbreviate sine, just SIN, cosine is just COS, and tangent is just tan, the first three letters, right? So easy enough. So these are functions, okay? So these are all functions on your calculator. There's buttons, just like log, right? So they're just buttons on your calculator. They're functions that do specific things. And a little bit different from log. We're going to get to know what each of these things actually does specifically. So hopefully it makes a little bit more sense than the log did at first. But these are basically just specific functions, right? And specifically for right triangles. Okay, so let's get right into it. Let's get rid of this. So sine, cosine, tangent, all very different, and they have to do with angle size. Okay, so you're going to take usually what you do is you're going to take the sine, cosine, tangent of an angle. Okay, just like you take the log of a number, like I don't know, 10, right? You're doing the same thing, but now the function is called sine, and it's of an angle, theta. So you can put the parentheses there or not. It doesn't matter for now. So we take the sine. What the sine is as you know, in a triangle, we talked about how the right angle is across from the hypotenuse, right? So as you can see, all angles actually, so there's angle 1, here's angle 2. All angles are across from a side, okay? So you can go across from a side. So angle 1 goes here, angle 2 goes here. And you can also be right next to a side, of course, right? So if I'm angle 1 here, the side next to it is right here, because this is always the hypotenuse, right? And so in green here is the side that's opposite of it. So it's just a matter of grammar, right? Just understanding what each side is. So the sine, if I take the sine of an angle, what that means is that I'm gonna make a ratio. This is not, I don't want green. I'm gonna make a ratio, right? They're all ratios. I'm gonna make a ratio. So I have a numerator and denominator. The numerator, the top, that's gonna be divided, is the length of opposite side. Okay? So the numerator, you just look across from the angle, the opposite side. And the sine, what you're dividing by is the hypotenuse. So that part is nice and straightforward. You're dividing by the hypotenuse. So this is always going to be less than 1, right? Because the hypotenuse is the biggest side. It always is. So if you're taking the length of the opposite side of this angle, it doesn't matter what it is. It's always going to be lower or shorter than the hypotenuse, because we know in a right triangle the hypotenuse is the biggest. So that's the sine. That's it. So we'll practice that. Hopefully that kind of makes sense for now. So now let's say I take the cosine, right? Now the cosine is very different, but also kind of similar. Then if you take the cosine of an angle, the numerator is instead going to be the length of the adjacent side. So hopefully we're using our English skills here. Adjacent means right next to, right? Right next to. So right next to is adjacent, okay? And that's obviously that's the only side left, because the hypotenuse is always the same. So it's whatever side is not the opposite, okay? And in the cosine, the similarity is that you're dividing by the hypotenuse again. So that kind of helps, because there's a little bit of a pattern there. The sine, you take the opposite side, opposite. The cosine, you are putting the adjacent side on top, okay? Cool. Again, these are buttons on your calculator, so for, most of the time you can just press those buttons, but you do need to understand, like, when you can't press those buttons, you definitely need to know what the functions are actually doing, like what these actually mean, so that you can calculate them, right? All right, and then one more. Let's get rid of this. One more, the tangent. So hopefully you're thinking, okay, well, what could be left? Well, the tangent is then this ratio. It does not involve the hypotenuse at all. So what you're doing for tangent is you're taking the length of the opposite, and you're going to divide it by the length. There's only one side left if we're not going to use the hypotenuse, right? So you're going to do the length of the adjacent. And that's that. So again, if this is not super clear, it's okay. We'll do some examples just to see, but let's just like soak in the English of it, right? So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent is opposite and adjacent, okay? So there are only 3 sides, so it's not super difficult. Or it's pretty easy to keep them straightforward, I think. But again, it's just kind of knowing. I mean, the difficult part is really just soaking in and knowing which one involves which sides, right? So before we get to an example, though, let's just here's something that I think all people in life pretty much who learn this stuff in high school, they learn this mnemonic. Mnemonic, is one of those like acronym type things or catchy phrases to help you remember something. So for sine, cosine, tangent, the mnemonic is not like real words, but it's pretty catchy to help you remember it. So sine, okay, we're gonna do cosine and tangent. Okay, so SCT, right, for sine, cosine, tangent. Get rid of this distracting stuff up here. All right, so this is how you're gonna remember it. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And the tangent is the opposite over the adjacent. So these are not real words, at least I don't think so. But you pronounce this SOHCAHTOA, okay? So nice little like I don't know, some expression you might make if you're angry or something. But SOHCAHTOA, and that's just again just to help you memorize what each function is dealing with. Again, we're getting the O for opposite, the H is hypotenuse, and the A means adjacent. So this, use this, say it to yourself before bed, before you eat dinner, like whatever you need to do to memorize this. But hopefully this helps you remember what each function does, right? Sine, so we got, sine, opposite, hypotenuse. And the only part that this doesn't cover is the ratio part, but that you can, just keep in your head that it's a ratio, right? Cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Okay, SOHCAHTOA. Everyone learns that. So I definitely did when I was in high school. All right, let's actually do an example. Something more interesting. All right, let's get a triangle here. Let's get our famous triangle that we all like, the 3, 4, 5 triangle. Yeah, if you didn't hear this before, right? 3, 4, 5 triangle is just a Pythagorean triple. It's called. It's you can start to memorize this as a right triangle no matter what. So if you see 3 and 4 and a right angle, you can just automatically know that hypotenuse is 5. If you see 3 and then 5 and is across from a right angle, you know the other side is 4. So that's just something you can start to memorize. So let's put, again, when we talk about an angle, we use theta as our symbol. So let's put theta here, right? Because there are only two spots for our other angle, right? Because we've got the right angle down here. So there are only 2 other spots for the theta to be in the corners. But let's put it right there. So based on where theta is now, we need to do the sine, cosine, tangent, right? So sine, the sine of theta, okay? Well, SOHCAHTOA. So sine is the opposite side, opposite over the hypotenuse. Abbreviated them there, all right? Well, that means that opposite of theta, right, where theta is 4, okay? See that? And the hypotenuse, of course, we know is 5, right? So therefore, we just fill in the blanks. That means the sine of theta is just 4 over 5, 4/5. Easy money, right? That's it, literally. Obviously, you know, you'll have times where this fraction here can be simplified sometimes, but in this case, it definitely cannot be. So we don't have to worry about that. Sweet. Let's do cosine now. Cosine theta. Okay, now we're looking at adjacent over hypotenuse. Okay. Well, here's theta. Adjacent to it, the side right next to it is right here, the 3. And the hypotenuse stays the same. It's 5, right? It's always this. It's always the same. So there we are. So that means that cosine of theta is 3 over 5, 3/5. Boom. Nice. And then lastly, separate these out a little bit. We're going to do tangent. That's the last one. Tangent does not involve the hypotenuse. So tangent, we're looking at opposite, which is the 4 again, and then adjacent, which is the 3 again, right? So opposite over adjacent. So that means the tangent of this theta in particular is 4/3. Awesome. Good job. Yeah, and that's for this theta, right? If theta was in the other corner here, things change, obviously, right? Because now the opposite sides are different. The only thing that doesn't change is the hypotenuse, of course. That's that. Sweet. Let's do just another example just to make sure we're awake, because I am not fully awake right now. Just kidding. I'm fine. It's just a little bit late. All right. So let's do this. Let's do another triangle here. A little bit. Oh, that's not straight line. A little bit different numbers. All right, not that great of a triangle, but here we are. It's a right triangle. This shorter side is going to be 15. This leg is 36. And the hypotenuse across from the right angle, excuse me, is 39. So same deal. We're going to put theta down here in the bottom corner. So now we can set up all our 3 ratios, right? Let's start with sine. SOHCAHTOA, sine is opposite over hypotenuse. So opposite 15 right here. And hypotenuse we said was 39 because it's across from the right angle. It's the biggest, the longest, largest number, right? So that we don't really have to check for. Let me get rid of these dots. So we have opposite is 15 over hypotenuse, just 39. And again, you do a quick check to see if this can be simplified, because we're dealing with bigger numbers this time. And this actually can be simplified because 15 and 39 are both divisible by 3. So your actual final answer is going to be 5 over 13, 5/13. All right. So that's the fully correct answer, right? Always simplify your ratios or fractions. Let's do cosine now. Cosine theta. SOHCAHTOA, the ka part is adjacent over hypotenuse, and adjacent of theta is just one right here, right next to it, 36. And of course, we know that the hypotenuse is still 39. So let's fill that out. Here we go. 36 over 39. Again, you check, can this be simplified? It can. Both divisible by 3 again. So we're going to change it to 12 over 13. And last but not least, tangent. We're not dealing with hypotenuse anymore, so we're going to do opposite. Boom, 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 boom. 15 over adjacent, 36. Okay, so 15 over 36. And that, can it be simplified? Yes, it can, of course, again, right? Because we already knew they were both divisible by 3. So this is going to be 5 over 12. Boom. Not bad, right? That's that. And that's, you know, like the first level of problems you'll have to deal with. So that's that. All right. Let's get into some different stuff now. Let me just get my notes in order here. So let's kind of talk about special ratios. You know, you can call these the special right triangles. I mean, that's what they're called, but yeah, I mean, they're called the special right triangles. You can call them like the special ratios too. These are just these are again ones that you're going to want to memorize, or ones that you'll see very common. So memorizing them, knowing them will make it a lot easier, and you'll deal with it a lot more in geometry and maybe calculus and beyond too. So, so special right triangles. So what this means is that we have right triangles that you'll see more often, of course, and that means the ratios are going to be consistent, right? Remember, a ratio is just a fraction, right? It's just like, you know, a ratio. There are twice as many dogs as cats, right? So it's that. Let's deal with that, right? Let's say there are twice as many dogs as cats, right? So it's 2-to-1 ratio, right? That doesn't mean that there are exactly 2 dogs and 1 cat, right? That just means that whatever the number of cats there are, is that the number of dogs has to be double that. So the whole point I'm trying to make, right, is that ratios can apply to any number. The base form is here, 2-to-1. It's the most simple, right? The simplest form of it. But this base form can apply to all sorts of numbers as long as it satisfies that same fraction or that same ratio, right? So I could have 150 dogs. And if I follow the ratio, that just means I have to have 75 cats, right? So, yeah, so that's what I'm trying to say, is that they're a fraction, right? And we know that fractions can be simplified. So if I say that something is 1/2, and it's, you know, I proportion it out and say, okay, well, now I'm dealing with another thing that, you know, some other building, let's say, where the length or the height of it is actually 50. Well, if the base width is 1 and 2 height, now that I'm changing the 2 to 50, well, this should be half of that. So this is 25, right? So again, it's all about fractions and ratios. So now let me show you why I went on that tangent. No pun intended. Here we go. So here's the first special right triangle. There's our right angle. So the first special right triangle deals with the fact that the other 2 angles are equal, which means they have to both be 45 degrees. Okay. This is very special, right? So you've got the right angle here, okay, and then your 2 angles are congruent, or they're equal. They split up in half. So again, this is the base form. So what that means is that the lengths of the sides or the legs are going to be 1, and that means you do a quick, like, Pythagorean theorem. The hypotenuse has to be square root of 2. Okay. Unfortunately, not a whole number. You know, not a rational one, but square root of 2 always. Okay. So what that means is that, so how this helps us is now we can figure out those 3 functions, those 3 ratios, right, for 45. If our theta, so we're saying that theta, in this case, theta no matter what equals 45, because if I go here or I put theta there, it's the same, doesn't matter. So theta is going to be 45 no matter what. Excuse me. So now I know for sure, well, let's do our ratio. So now that I know that the sine of 45 has to equal what? Well, it's opposite, so, right? SOHCAHTOA, so it's opposite over hypotenuse. Well, the opposite of 45, doesn't matter which 45 is going to be 1, okay? As you see in the picture. And the hypotenuse, we know, is square root of 2. So no matter what, and you can enter this in your calculator, you'll get some decimal, right? But if you, which is not super helpful, but if you check your work by dividing 1 over square root of 2, it'll be equal. And just as a quick sidebar, we don't want these radicals, these square roots in the denominator. That's the rule, right? So this is you rationalize this real quick, and this is just equal to square root of 2 over 2. Okay, so this is what we actually use here. So the sine of 45 is the square root of 2 over 2. Guaranteed. That's a fact. Okay, now let's do the cosine. Well, the cosine is nice because it's actually the same exact thing, right? Because both legs are 1, so this is just also 1 over square root of 2. Or the adjacent side, doesn't matter which, is always going to be 1. And we know, again, that's just square root of 2 over 2. Again, you can enter these on the calculator, and you can enter square root of 2 divided by 2 over a calculator. It's going to be the same number, same decimal. And then last but not least, this one's nice and easy. Tangent of 45. Doesn't matter, right? But because we're not dealing with the hypotenuse, we're just dealing with 1 is going to be the opposite side of one of them, and then the adjacent side has to be the other one. So this is just 1 over 1, which is, of course, 1. So these are all nice little ratios that you can deal with and memorize, hopefully. And if not now, eventually. So that's the first one. All right. There's only one more, so not too bad. Okay. I'm gonna make sure this is big enough to write it. All right, so this is the next special right triangle. Our right angle is right there. Okay, sorry, that's not super neat. Now, instead of 45 and 45, you can tell, obviously don't always trust the scale, but you can tell it's a little bit different in size. So now, instead of 45 and 45, the other two are going to be 30. This one down here in the corner is going to be 30. And then this bigger one here up top is going to be 60. So this is another special situation that you can look out for. So this is the case. Well, what that means is this shortest leg here is going to be 1. The longer leg is another irrational number. It's the square root of 3, right? Which is like 1 point something, right? I think 1.7 or something, rounded. And the hypotenuse, if you do the Pythagorean theorem real quick in your head, the hypotenuse therefore has to be 2. Cool. So, yep, and we're just going to do the same thing, right? So let's start with let's just start with the sine. So now we have 2 different situations, right? Because in the last special triangle we had 45, 45, so it doesn't matter which one is theta. You're going to get the same ratios, right? But now we have 2 situations, but that's fine. Just a little bit more to memorize. So let's say that, let's do the sine, right? So the sine, let's say theta equals 30. So that means the sine of 30, no matter what, is going to equal its opposite over hypotenuse. The opposite of 30, if we look in our diagram, is 1. Boom. Okay. Cool. And the hypotenuse, we know, is 2. Always 2. So the sine of 30 is just 1/2. Pretty nice. Let's say theta is now 60. Well, now we can say that the sine of 60 is opposite of 60, in this case, is square root of 3. And of course, the hypotenuse is the same, so it's 2. So now sine of 60, we can always say square root of 3 over 2. So that's the sine. Cool? All right, let's do cosine. So now let's say that theta, again, is 30. Well, that means the cosine of 30 has to equal, we're going adjacent, right? So here's 30. Adjacent to that is right here, square root of 3. So you'll start to see the pattern here. So cosine of 30 is square root of 3. Hypotenuse is 2, so over 2. So hopefully you're recognizing the pattern. So now let's say theta is 60. Well, that means the cosine of 60, in this case, it's different, right? 60 is here, so next to it is 1. So now that adjacent is 1 and the hypotenuse is 2. Boom. Now, hopefully you notice the pattern there, right? Let me fix my numbers here. That they just switched, right? So here the sine of 30 was 1/2. But now if I do the cosine of 60 is going to be also 1/2 because the sides are shifting, right? Opposite of 30 is 1, but adjacent to 60 is also 1. So now hopefully you see how those two things connect, right? So let's just finish our last one real quick. Our tangent, if theta is 30, that means tangent of 30. We're dealing with opposite over adjacent, right? So we know opposite of 30 was 1, adjacent was square root of 3, 1 square root of 3, and we rationalize this real quick, and this is actually just square root of 3 over 3. So that's the final one, final answer there. Now instead of we're doing 60, the tangent of 60 is opposite, which was square root of 3. And next to 60 is 1. So this is just square root of 3. That one's easy. Nice and easy. Cool. Yeah, so, screenshot this, whatever you need. But these are also in the notes. So you can just download those and look at those. All right. So let's put this into action, actually. Let's actually do an example of this just so you can see how, at least one specific case where this is a little bit useful, right? So let's give our triangle here. Here's a right angle. I don't know, you could make this a word problem too. You could say like this is some part of like a field or a park that, the county is trying to build or something. Let's say this is like 100 meters or so, okay? Let's close to the sidewalk, right? Part of the park close to the sidewalk. They want to know how long this end has to be, okay? This end, let's say this end is near some houses. They want to know how long it should be to fit within there. And we know for sure that this angle down here that connects one of the legs to the sidewalk is going to be 60 degrees. And so hopefully like right away, a flag goes in your head, right? Where it's like, okay, well, this is a special triangle. So this is kind of nice. I actually don't have to do a whole lot of my own work here because the ratios are already done for me. So the unknown is x, right? This is our unknown. We're trying to figure that out. And we know that the hypotenuse, because this is the right angle, the hypotenuse is 100. Okay, so this is hypotenuse. So yeah, so we know from the special right triangle that those notes I just wrote, we know for sure, well, the sine of 60. And we want to use sine because here's 60. Well, if the unknown is x, if I follow all the way to x, I'm like, okay, well, across or opposite of 60 is the unknown. So I should obviously use sine here, right? Cosine is not going to help me because I don't really care about this side right now. So I'm going to use sine. So sine of 60 we know has to equal, if you look from the previous notes, square root of 3 over 2. And that's the base form, the base ratio, right? Well, in this case, in this triangle, this is the base ratio that we just talked about. Well, in this case, for this triangle, we can say that the sine of 60 is going to equal the opposite, which is x, and the hypotenuse in this case is 100. So all we have to do, like with all ratios, you just set them equal to each other to figure it out. So we have our two ratios here. Set them equal because they both equal sine 60, right? So square root of 3 over 2 equals x over 100. Cross multiply, 2x equals 100 times the square root of 3. Divide by 2, divide by 2. Final answer, x equals 50. And then you keep that square root of 3. And if this was a word problem, of course, you don't want to forget your units. So x equals 50 square root of 3 meters. And leave it like that, right? Don't go change it to a decimal because that's not as pretty or nice. So that's like one instance where you'll use those special right triangles. Awesome, yeah. I don't know if we'll do too many of those for now, but I think your homework might have a couple of them. But anyway, in the notes you'll see the reciprocal functions. So just look over those, read the book for those. I won't really go over them. Maybe, if you have questions about them, let me know. I can certainly make another video or talk about them for a few minutes. But I just want to do a couple more practice problems just because I think that's more useful, at least for, a video I'll post. So here are some different situations that we haven't really covered, right? They're a little bit less obvious. So let's say, I have a triangle that's not big enough, sorry. Using my iPad, so I have to write with my finger, which is, of course, not the easiest thing to do. So let's say that we got two unknowns in this case, right? And then right here is an angle, and it's 50 degrees this time, okay? I should really get a stylus, I just realized. Anyway, so again, no flags going off this time, right? So you think to your head real quick, well, is this a special right triangle? It's not, right? So you can't use that quick shortcut that we just did for the last problem. So 50, that's okay. But again, these are in your calculator. So you can certainly use that to help you in this case, at least. We know for sure the hypotenuse is 15, right? That is across from the right angle. So the hypotenuse is 15. We have two unknown sides. So in this case, we can't use the Pythagorean theorem, right? Because we have two unknown sides. We don't have just one. So we can't use the Pythagorean theorem. So we have to rely on our trig functions / ratios. So let's just set them up, right? Our theta is 50. That's the only one given to us, so we have to use that. You can deduce the other one, right? Because if all angles add up to 180, I mentioned that last time, that means this one has to be 40, right? Because you have 90 plus 50 is 140. 140 plus another 40 is going to be 180. But why do all that extra work, even though it's quick? We already have a 50 given us, so let's just use that. The trig functions and ratios, those three, sine, cosine, tangent, are built to help you get what you need, even if you only know one angle, right? So theta is 50. So let's do, our two unknowns happen to be the opposite side, x, and then adjacent to 50 is y. So now we can use that to our advantage, right? So let's start with sine. So if the sine of 50, or theta, but sine 50 has to equal x is the opposite side over 15. Well, now this is where your calculator comes into play, right? So this right here, this you just enter in your calculator, okay? You enter this in your calculator and make sure it's into degree mode because we have 50 degrees. You'll get something, obviously don't round it, just use it in your calculator, but you'll get something like 0.766 something, right? And this is going to equal x over 15. And now this is just algebra at this point, right? You're just solving for x. So to get rid of x, or to isolate x, you just multiply by 15 on both sides, right? So now your calculator you're just entering this times 15. Let me clean this up a little bit. and you'll get, and now this is where you can round depending on what the problem asks you. I rounded to the nearest 10th, so you'll get something like 11.5. So not too bad, actually. You're going to use your calculator for this, so it's not terrible. Now to get the other one, y, we're going to set up the cosine. Let me actually get rid of all of this just to make it cleaner. So now if we set up the cosine of 50, this is now going to equal y over 15. Again, you enter this in your calculator. Calc. You'll get, let's see what I wrote here. So 0.6427 something equals y over 15. You multiply by 15 to get y by itself. Y is going to approximately equal 9.6. So a little bit different of a different problem, but one that's super common, right? Where you don't know two sides and you have to use one of the angles to figure them out. Okay, sweet. Let's just do one more. Yeah, let's just do one more real quick. Again, just takes like another extra step of work. I think this is one that's going to be in the notes again too. Right triangle, 18, 80, and that's it. And then we're going to put theta right here. All right. So I actually want you to find, in this case, we don't want to know what the angle is. We want to know what sine, cosine, tangent are of that angle. Okay. Well, hopefully you're saying, well, something's wrong here. In order to find sine, cosine, tangent, we need this other sign, and we don't have that. Well, guess what? You have the Pythagorean theorem. And so again, now you have all these tools. And again, it's just like always in math, it's just figuring out what tools you need to use at what time, right? You have two sides. That's all you need to figure out the third one because we have the Pythagorean theorem. So if we do that real quick, 18 squared plus 80 squared, we don't know the hypotenuse, right? Because it's across from the right angle, equals c squared. This is 324 plus 6,400 equals c squared. C squared equals 6,724. Thankfully, this is a perfect square. C equals 82. So I'm just going to put 82 up here because we just figured that out. And now the rest is history, right? It's just kind of back to the examples we did a few minutes ago. So this is not anything crazy. It's just kind of realizing, you do have that extra step to do before you can get what you want. So now we just set these up. Well, that means the sine of theta, in this case, is opposite. Opposite is 80. The hypotenuse is 82. This can be simplified, right? So hopefully you notice they're both even numbers. So this is 40 over 41, final answer. Cosine theta, adjacent of theta is 18. Hypotenuse 82. Again, both even, 9 over 41. And then the last but not least tangent is opposite, 80 over adjacent, 18, which is 40 over 9. So I just looked at my drawing for all of these, right? Just like the first couple of examples from a few minutes ago. Hopefully that wasn't too fast. Again, just rewatch the video if you need to. Look at the notes that I'll post online. I think I have time. My laptop's about to die actually, but I think I have time maybe to do a quick, try to do a quick word problem actually, because you do have one for homework, and I think word problems are really the whole reason we learn this. Because believe it or not, geometry is super applicable to life, right? And word problems are, especially with right triangle geometry, the word problems are super important because you can use them in so many different cases. Lots of architects use them, engineers, all sorts of engineers have to use these ratios. even like pilots, even, you know, or people who work in the tower for like airlines and stuff. Um, what else? I mean, there's so many applications, so it is kind of nice. But let's try to do a quick problem from the book. I wish I could cast it up here. It's a little bit more difficult. So I'll just kind of read it to you. So here's the drawing. Okay. I've got a right angle here. And this says 12 inches. And then this says 17 degrees. And this is L. So unknown, right? So the word problem says a skateboard ramp, okay, a skateboard ramp will have a height of 12 inches. So that's right here. Cool, skateboard ramp. And the angle between the ramp and the ground will be 17 degrees. So this is a really cool example, right? This is a real situation. This could easily be a real situation. The angle that the ground makes with the ramp is 17 degrees. So even without the picture, you could kind of draw this yourself, and you'll have to get used to that. That's like, those are I think the more fun examples when you try to figure out the visual yourself. More fun, but also could be harder depending on if you like that or not. Anyway, to the nearest inch, what will the length of the actual ramp be? So that's what this L is, right? We don't know the length of this actual ramp, right? So that's what we're trying to figure out. But we know the angle it makes with the ground, and then we know the height of it at the top of the ramp. So that's really helpful. So if we're trying to figure out, well, this is all you need are your trig ratios, right? So you're going to use, you look real quick at what you have. Well, I have 17 degrees. The side I do have is across or opposite of it. So if I just set up real quick sine of 17, that means it's opposite of our hypotenuse. The hypotenuse was the unknown. So this is perfect because that means that it's 12 divided by L. Well, this is a little bit different from the problem that we just did a couple minutes ago. This, again, you enter in your calculator. So calculator, and you get, let me calculate it real quick. Sine of 17 is, boom, something around 0.2. Again, just leaving your calculator. I'm just writing it to show you. 3 ... Okay, and this is going to equal 12 divided by L. Well, the rest is just algebra, of course. All you have to do, so you're going to have to move things around a little bit. You're going to multiply by L on both sides to get L on this side. Okay, so if we rewrite that real quick, we'll have L times that random number, that random decimal, 2923, ... is now going to equal 12. And to get L by itself, you just divide by this, which was the sine of 17, right? So lo and behold, so let's redo this now. I'm actually going to rewrite it as the sine of 17 because now that hopefully you're comfortable with just putting that in your calculator. So now L, we figured out, equals 12 divided by the sine of 17. You just enter that in your calculator. So let's do 12 divided by that, and I get, and let's just round to the nearest whole number. I got approximately 41. And then let's put our units, inches. Boom. Not bad. So it's just like the examples we did without a word problem, but the only hard part in this case is going to be figuring out, again, just with word problems always, is just translating the English to math. So hopefully not too bad. Let me know if you have any questions. Hopefully you like this stuff more. If not, I'm sorry, but it will, hopefully you do find some use to it with at least the real life application. But let me know if you have any questions or if you need any help, and talk to you soon.